Hey guys, welcome to our first lecture of 3 electrochemistry lectures that we're going to do. Just a reminder that this unit is one of the units that was canceled from like the AP exam that they cut out for this year because of this coronavirus mess. But the SAT subject test, which if you guys ever take SATs again, this is a really big topic on the SAT chemistry subject test. So I hope you're joining us, or thank you for joining us, because obviously if you're watching this, you're joining me. And let's chat about it, because honestly, this is super fun little unit here. It's taking into account some of the things that we learned in chapter 4 about oxidation and reduction reactions and assigning oxidation numbers. Hopefully you remember how to do that. And it lets us take a look at how redox reactions can be used to do work. And by work, I'm talking about electrical work. So electrochemistry is the study of relationships between chemical reactions and how those chemical reactions can produce a flow of electrons. And you guys remember from physics class that electricity is a flow of electrons. That's what electricity is. Okay, so the types of reactions that can produce this flow of electrons are called redox reactions, and that stands for oxidation and reduction reactions. And oxidation and reduction reactions are simply reactions where electrons are transferred. Now, not all reactions involve a transfer of electrons, but any reaction where electrons are transferred from one species to another are in fact we call redox reactions. These aren't new to you guys. In fact, we could just take a look here down below at this zinc and hydrochloric acid reaction. And this is a reaction that you guys are super familiar with, and you would consider that to be a single replacement reaction, which it is. However, we can also call this a redox reaction. And one of the ways that we can identify whether or not electrons are being transferred in the reaction is if there is a change in oxidation number between the species. Now, we learned about assigning oxidation numbers way back in chapter 4. So if you don't remember the rules for assigning oxidation numbers, or if it doesn't sort of click back into your brain as we go through it in this example, then definitely go back to chapter 4, page 100 and something, and look up those rules again. So I'm going to go ahead and assign oxidation numbers to this reaction. Elements in their standard states have oxidation numbers of 0. Hydrogen is a +1. Chlorine is going to be a -1. These guys have to add up to 0 in a neutral compound. My chlorine is a -1. If there's 2 of them, that means my zinc is a +2. Hydrogen element in its standard state, oxidation number of 0. Okay, so we can see in this reaction that there is a change in oxidation numbers. And you can see that zinc is going from a 0 to a +2. If it's going from a 0 to a +2, that is happening through the loss of electrons. We call the loss of electrons oxidation. We can also see that there is a change in oxidation number in the hydrogen. What color should I use for that? Let's do red. All right, so my hydrogen is going from a +1 to a 0. How is it going from a +1 to a 0? It must have gained electrons. And we call the gain of electrons reduction. Now, we can remember that oxidation is the loss of electrons, And reduction is the gain of electrons through two different methods. One is Leo the lion says Gur, which is the one I always sort of remember, loses electrons oxidation, gains electrons reduction. But I know a lot of you guys prefer oil rig. So either one of those is fine. Oxidation is loss, reduction is gain. So just remember that oxidation, as far as a definition goes, is the loss of electrons. And I can represent that loss of electrons with what we call the oxidation half reaction. So if I wanted to show this zinc going from a 0 to a +2, I would show that oxidation like so. My zinc solid is becoming zinc 2 plus aqueous plus 2 electrons. And you can see here in this half reaction that my electrons are on the right-hand side for oxidation, showing the loss of these electrons. And you might also notice that my charge cancels out, right? So if I have 2 electrons and a 2+ charge, that will equal a neutral zinc. So always remember for your oxidation reactions that your electrons appear on the right-hand side of your equation. Let's talk about reduction. Reduction is the gain of electrons. In this reaction, I should probably scroll back up, the thing that is gaining electrons is my hydrogen. My hydrogen 1+ ions in my HCl are becoming diatomic neutral hydrogen gas over here. So if I was to write my balanced reduction half reaction, it would be the 2 hydrogen ions in solution are gaining 2 electrons in order to become neutral diatomic hydrogen gas. So notice in my reduction half reaction, the electrons appear on the left-hand side because they are being gained by the 2H+ aqueous ions. And so you see your 2+ charge here and your 2- charge there, cancels out with a neutral hydrogen gas. And if we were to actually combine these reactions into an overall reaction, we would just end up with the net ionic equation of the reaction that we were looking at up here at the top, with the chlorine being your spectator ions. So did I leave myself enough room? Oh yeah, because I think I went off to the side, so I can just keep scrolling down. All right, so let's write that overall net ionic equation, shall we? If I combine these two equations, we would end up with an overall reaction of zinc solid plus 2H plus aqueous becoming Cn2 plus aqueous and H2 gas. This is my overall net ionic equation for the redox reaction or single replacement reaction between the zinc and the hydrochloric acid. And what you'll see is that my chloride ions do not appear because they are spectators, and nor do my electrons, because the number of electrons that were lost by the zinc were gained by the hydrogen. So these numbers of electrons need to be equal or balanced and cancel out in these redox reactions. However many electrons you lose needs to be equal to the number of electrons that you gain. And obviously that's just going to come into play with our coefficients of our balanced chemical equation. So in this reaction, when the zinc was being oxidized, it was allowing the hydrogen to be reduced. So because the zinc was allowing for the reduction of the hydrogen, we called the zinc solid the oxidizing agent. The zinc, no, Oh my God, I'm gonna screw this up, you guys. I wish I could rewind. I probably can, but I'm not that slick yet with my recording software. Let me say that one more time. Because the zinc is being oxidized and allowing for the reduction of the hydrogen, we call the zinc solid the reducing agent, which is weird, right? So the thing that gets oxidized is the reducing agent. The book also calls it the reductant. I usually, everything I read always tends to say reducing agent. Same thing, reductant or reducing agent. It allows for the reduction of the other species. So the thing that gets oxidized is the reducing agent. And this thing that is being reduced is allowing for the oxidation of this thing up here, the zinc. So in this case, the HCl, which is where those aqueous H plus ions came from, the HCl is the oxidizing agent. So you just have to remember that the agent thing is reversed. The thing that gets oxidized is the reducing agent. The thing that gets reduced is the oxidizing agent. I kind of like this. It's super logical, right? Assign your oxidation numbers. Look for a change in those oxidation numbers. Going from a 0 to a positive meant the loss of electrons, and so the loss is oxidation. Going from a positive charge to neutral would be a gain of electrons, and that is reduction. Now, these changes in oxidation numbers don't always have to be to 0. Like you could have something going from a +1 to a +2, or from a +2 to a +4. So you can, or negative charges, or oxidation numbers, I should say. So you can just have changes in magnitude of the charge. It doesn't always have to be going through a neutral oxidation number of 0. Okay? So I think that's all I wanted to talk about in terms of just a review of what an oxidation reduction reaction is and identifying oxidizing and reducing agents. You know what? Let's do a practice. That would be fun. Let's do that. Okay. So I would like you guys to practice this like we were in class. I'm going to give you a reaction and then I want you to pause the video to see if you can identify who's being oxidized and who's being reduced. So let's say we have the reaction of solid plus, sorry, I probably should have already had this. NiO2 solid plus 2H2O liquid becoming cadmium hydroxide solid and nickel hydroxide solid. Oh shoot, didn't write small enough. Okay, so what I would like you guys to do is pause this video now. I want you to go through and assign oxidation numbers, look for the change in oxidation numbers, see if you can figure out who's being oxidized, who's being reduced, and maybe write those half reactions out and identify oxidizing agents and reducing agents. So I'm going to let you guys go ahead and pause the video right now. All right, welcome back. Let's assign our oxidation numbers and see how you did. Elements in their standard state have an oxidation number of 0. Rule for oxygen. Oxygen is typically a -2 oxidation number, unless it's in peroxide. And so if this is a neutral compound overall, that would mean my nickel had to be a +4. Again, oxygen is usually -2, which means my hydrogen in the water has to be a +1. Here, I know that this is a polyatomic ion with a 1- charge. So the oxygen, if it's a -2, means my hydrogen is a +1. which gives me that -1 charge overall for the hydroxide. If this is a -1, and there's 2 of them, that's a 2- overall, so my cadmium is a +2. And over here, my hydroxide again is -2 and a +1. And oh, you guys, I'm such a jerk. You probably had a hard time with this because I didn't put this. Oopsie, sorry. I didn't put the subscript of a 2 on the outside of my hydroxide, which would have screwed you guys up on assigning your oxidation number for the nickel. So because I didn't have that 2 there, you probably said that the nickel was a +1, but there was supposed to be a 2 there. Sorry. Okay, that's a simple fix. So our nickel here would be a +2. You know, teachers trying to talk chemistry on Sunday mornings. It's not always the best. All right, do you forgive me? What color did I use? I think I used blue. Let's double check up top. I used blue for the oxidation or the loss of electrons. Okay, so let's find the oxidation or the loss of electrons. We can see here that the cadmium is going from a 0 to a +2. So that, in fact, is my loss of electrons. This is a loss or loses electrons. This is my oxidation for this reaction. And then I think I used red. My nickel is going from a +4 to a +2. So there's one of those examples of where your charges or your oxidation number is changing but not going to 0. So if we're going from a +4 to a +2, that means it must have gained electrons. And that is reduction. If I wanted to write out these 2 half reactions, cadmium solid is becoming cadmium 2 plus solid through the loss of 2 electrons. So this is an example of oxidation. And then the other half reaction is the nickel solid with a 4+ charge, gaining 2 electrons to become nickel solid with a 2+ charge. And this is reduction. So if we were identifying our agents in this case, the cadmium, because it's being oxidized, is the reducing agent. And the nickel oxide reactant with our nickel 4+, because it's being reduced, is my oxidizing agent. So we usually refer to the entire species that's in the reactant. Like I wouldn't say like the nickel 4+, I would say the nickel oxide, this whole substance. This whole substance is what's considered to be the oxidizing agent, and this whole substance, just the element, is your reducing agent. So hopefully you were able to do that. And we can see here that the hydrogen and the oxygen in here, their oxidation numbers did not change. And so those were just spectators in this reaction. Now, we wouldn't have like a net ionic equation here because everything here is solid or liquid, so we wouldn't typically write this as a net ionic equation. But if we wanted to see really the only things that were involved in the transfer of electrons, it would just be the cadmium and the nickel. Okay, so for these last 2 reactions that we looked at, balancing these reactions was pretty easy. Like you could just, if I had given you an unbalanced equation, you could have just very easily balanced it by throwing your coefficients out in front. Unfortunately, balancing redox reactions often gets much much more complicated. And so we have a set of rules that we use in order to balance redox reactions as they get more complicated. So if you've had enough of your notes for now, maybe here's a good time to sort of take a break, because this takes a little bit of brain power here. But it's a bunch of simple, easy rules to follow. But it's like a logic puzzle. So anyway, so if you want to take a break and come back in a few minutes. Otherwise, let's just keep rolling right along here. This is how we balance redox reactions. The first thing we have to know about a redox reaction is whether it's taking place in acidic solution or in basic solution. You might be asking yourselves, why does it need to be acidic or basic at all? In order to facilitate the transfer of electrons, most of these reactions happen in charged solutions, or solutions that have an excess of H plus or an excess of OH minus. So if it's an acidic solution, obviously we know that that's an excess of H plus in solution, and if it's basic, it means we've got some extra OH minus in solution. So let's go ahead and start by balancing in acidic solution first. Okay, so this reaction is going to be in acidic solution. It just affects our rules slightly, and you'll always be told whether or not the reaction is in acidic solution or in basic solution. Okay, do you guys like how I learned how to type into this too? Fancy, trying to get better. All right, step number 1 says divide the equation into half reactions. And by half reactions, I'm just referring to the oxidation half reaction and the reduction half reaction, which we were doing previously. Now, in order to identify the oxidation and the reduction, we obviously need to assign oxidation numbers. Okay, so the first thing I'm going to do is I'm going to assign oxidation numbers. So my oxygen here is a -2. If I need a 1 minus charge overall, that means my manganese is going to have to be a +7. Here my oxygen's a -2. So that's an 8 minus, which means and I need a net 2 minus, that means my carbon needs to be a +3. Here my manganese has a +2 charge, or +2 oxidation number, I'm sorry, to match that 2 plus charge. And here oxygen is a -2, and my carbon is going to be a +4. Okay, so I'm seeing my manganese going here to here, going from a +7 to a +2. If it's going from a +7 to a +2, that must be the gain of electrons. And so that's going to be my reduction half reaction. And I can see my carbon is going from a +3 to a +4. It's becoming more positive in charge. And so, oops, if my carbon is going from a +3 to a +4, that is the loss of electrons. And so that's my oxidation half reaction. Now, you might not have even needed to do all of that. Like, you guys can clearly see, like, the manganese is going to become a different type of manganese. So, like, that's one of your half reactions. And your carbon is becoming a different type of carbon-based compounds. That's your other half reaction. So you don't even necessarily have to go through all of that detail, but I thought it was good practice. Okay, so now that we have identified who's being oxidized, who's being reduced, we can write out these two half reactions. So MnO4 minus becoming Mn2 plus. And then my other half reaction is C2O4 becoming CO2. Okay, so there are my two half reactions. Step number 2, balance all of the elements except for hydrogen and oxygen. So if I'm looking up here, I'm balancing manganese with manganese, that's already balanced. So I'm just going to rewrite that. And once you get better at these, you're not going to need to write out every single step separately every single time. It does get a little tedious. I'm not going to, I'm going to do that for you now just so that we can see every single step. But if you didn't want to like rewrite something that you'd already written, you can sort of abbreviate. Okay, now I need to balance everything but hydrogen and oxygen in this half reaction. So I can see here I've got 2 carbons on the left and only 1 carbon on the right. So I'm going to balance this half reaction like so. 2 CO2. Okay. Step number 3, I'm going to balance my oxygens by adding water. I can't figure out how to make that a subscript. Something to work on. Okay, so I've got 4 oxygens on the left. So MnO4 minus becoming Mn2 plus. I need 4 oxygens on the left. So I'm going to add 4 waters to the right-hand side. And we can do this, you guys, because these reactions are happening in solution. So there's clearly going to be water present. This half reaction, I've got 4 oxygens on the left. And I have 4 oxygens on the right. So this guy's already balanced. So I'm just going to rewrite it. All right. My next step is to balance the hydrogens in my reaction by adding H plus ions. Again, I can do this because this reaction is happening in acidic solution. So if I look up here at my manganese half reaction, I see that I have 8 hydrogens on the right-hand side. So I'm going to need hydrogens on the left. So my MnO4 minus plus 8H plus becoming Mn2 plus and 4 waters. What am I doing? Balancing hydrogens over here. There are no hydrogens over here, so that reaction just stays the same. 2CO2. Okay, moving on. Now we need to balance charge. Because these are redox reactions, we can balance our charges by adding electrons to one side or to the other. I'm going to show you guys how I would look at the charge on the left versus the charge on the right here in this different color. So if I'm looking at my charge on the left-hand side of this reaction, I have an 8 plus here and a 1 minus here. So on this side of the reaction, I have a net charge of 7 plus. And on this side of the reaction, with my 2 plus here and my water here, I have a net of a 2 plus. I need to make these charges equal. And the only way that I can make them equal is by adding electrons to one side or the other. So in order to make these charges balance out, I can make this 7 plus equal to a 2 plus by adding to this side of my half reaction 5 electrons. So do you see how my 5 electrons plus my 7 plus charge will result in a net of a 2 plus overall on this side and the 2 plus overall on this side? In this half reaction, I have a 2 minus charge on the left, and I have no charge on the right. If I want to make these charges equal, I would need to add 2 electrons to this side. So you can see over here, I have a 2 minus charge now, and over here I have a 2 minus charge. So that is how we make charge equal, is by adding electrons. Now you better hope, if you've done everything correctly, that on one of your half reactions, the electrons are on the left because it's reduction. And in the other half reaction, your electrons are on the right because it's oxidation. So if you end up with the electrons on the same side of both half reactions, you did something wrong. So that's a good way to check to see that you're on track. So let's go ahead and write these half reactions, including those electrons now. So I'm going to look and see MnO4 minus. I'm going to have to start writing smaller so everything fits. 8H plus 5 electrons, becoming Mn2 plus and 4H2O. And this half reaction is going to be C2O4 2 minus, becoming 2CO2 plus 2 electrons. Now, we know that the number of electrons that are lost have to be equal to the number of electrons that were gained. So here I can see my reduction is of 5 electrons and my oxidation is of 2 electrons, and that's just not going to work because these electrons that are being gained have to be coming from the half reaction that's losing the electrons. So my least common multiple would be 10. So I need to make my electrons equal by adding these coefficients or multiplying through by a coefficient. So I'm going to have to multiply this reaction through by 2. I'm going to have to multiply this reaction through by 5. So let's go ahead and do that. All right, so I'm going to have 2 MnO4 minus plus 16H plus 10 electrons becomes 2 Mn2 plus 8 H2O. And if I'm multiplying this guy through by 5, I've got 5 C2O4 2 minus becoming 10 CO2 plus 10 electrons. So now my number of electrons that are gained is equal to my number of electrons that was lost. And now I get to combine and reduce. So this is the fun part where we put it all together. So here we go. See, I told you this was a fun little logic exercise. Let's scroll down. All right, here we go. I'm going to put all of my left-hand side stuff together. So I've got 2 MnO4 minus plus 16H plus 10 electrons plus what's on the left-hand side of my other half reaction, the 5C2O4 minus, and the right-hand sides of my reactions, my products, 2 Mn2 plus 8 H2O plus 10 CO2. Ooh, look, I made it fit. Plus 10 electrons. I just had like this horrible feeling of, oh my God, what if my thing stopped recording? Hang on, I'm gonna go check. Oh yes, thank God, we're still recording. That would be terrible if I had to redo this whole thing. All right, so now we get to reduce. And by reduce, remember things that are on the same on the left side and the right side cancel out. So let's use a fun color. Cancel things out. It's yellow. All right, so my 10 electrons cancel. Beautiful. Oh, that's all that cancels. Sometimes these are much more fun, you guys, and we get to reduce waters, combine and reduce waters and stuff. But all that canceled out, and this was my electrons, so that was kind of lame. I'm not even going to bother rewriting it. Once these electrons cancel out, there's your reaction, you guys. Our 2 MnO4 minus plus 16H plus 5 C2O4 2 minus becomes 2 Mn2 plus and 8 H2O and 10 CO2. Probably I'll make sure. Yeah, we're right. That's it. Good job. You made it through. Ready to do it all over again in basic solution? I know you are. Let's really hope that I prepped this for basic solution as well. Oh my God, you guys, I didn't do it. I didn't prep it for basic solution. Okay, I can solve this problem. I'm gonna pause my recording. I think I can pause and restart. Okay, welcome back. Hopefully we're recording again now. All right, I'm trying all these new things, pausing recordings. Hopefully that worked. You didn't have to sit here and watch me. All right, now I'm ready with an example of balancing a redox reaction in basic solution. So here's my problem that we're going to work through, and this is going to be balanced in basic solution. The good news is that the steps are the same. There's only one additional step that we have to take. So let's go ahead and first identify our half reactions. And it's pretty obvious to me that my CN minus is going to need to be becoming my CNO minus, and my MnO4 minus is going to be needing to become MnO2. Now again, we could go through and assign all of our oxidation numbers and figure out what everybody is, but I think it's just, a little faster while we're focusing on balancing to just split into the half reactions based on what elements are present. So that's a quick and easy way to do that. All right, so I'm going to now write these things as my half reactions. So my first half reaction is CN minus. I don't feel like doing states of matter. I don't think I did states of matter last time. Let's keep it simple. Okay, so my CN minus becoming my CNO minus, and my other half reaction is MnO4 minus becoming MnO2. All right, step number 2, balance everything but hydrogen and oxygen. So on my left-hand side here, carbon, nitrogen, those are both balanced. Manganese and manganese, both of those are already balanced. I'm not even going to bother rewriting those. Those are already balanced on both sides. Okay, but now I need to take each of those half reactions and I need to balance my oxygens by adding water. So now I will go ahead and rewrite these. So my CN minus, I need some water. I need 1 water on this side to get my 1 oxygen balanced with my CNO minus on the right. And my MnO4 minus, do I keep sighing? I don't know, these balancing ones are like so methodical or zen-like, they calm me down. I just keep sighing. MnO2. And I need 2 more oxygens, so I'm going to put 2 water molecules over there on the right. Step number 4. I want to balance my hydrogens by adding H+. Now here's probably where you're like, whoa, Mr. Rivera, you said that the solution was basic, so how is it that we're adding H+? We're going to take care of that here in a second. So just stick with me. It's just a method that we use to get to the right balanced equation overall. Not that this is an acidic solution, this is the easiest tool to do it. So CN minus plus H2O, CNO minus plus 2 H pluses. Don't worry, we'll get rid of them later. And this MnO4 minus, I need 4 H pluses on this side to balance those hydrogens out. MnO2 plus 2, oops, running out of room. Okay, so I got my 4 H pluses, and over here I've got my 2 H pluses. Now here is where we are going to take care of the fact that we are in a basic solution. Okay, so right now we've got these hydrogens in our reaction, and we need to get rid of them because this solution is basic, so we should have an excess of OH minus, not an excess of H plus. So what I want to do is I want to take these H pluses over here, and I want to get rid of them. And the way that I would get rid of them would be by adding 2 OH minuses to the right-hand side of this reaction. Because we know, based on our acid-base chemistry, that H pluses plus OH minuses, these guys plus those guys, make water. So in fact, I don't really like the way I wrote that at all. Let's do it a little closer. So these H pluses I want to get rid of by adding 2 OH minuses to this side of the reaction. That is going to combine into making waters. It's going to make 2 water molecules. But if I add 2 OH minuses to the right-hand side of my equation, I need to also add 2 OH minuses to this side of my equation as well. I need to add OH minus So that's going to combine these guys into two water molecules. And I'm going to be left with two OH minuses over here on the left. So if I go to rewrite this half reaction, I would be at Cn minus plus H2O plus 2 OH minus. I just realized I lost my minus. And on my right-hand side now, I'm going to have CnO minus plus 2H2O. These guys became water, right? These two guys combined into two water molecules. So that's how we get rid of those H pluses that we don't like, because it's in basic solution, not in acidic solution. And so here's my base now. Let's do that same thought process to the other half reaction. So I've got these 4 H pluses here that I don't like. So I want to add 4 OH minuses to neutralize them. And again, those are going to make waters. But if I add 4 OH minuses to the left-hand side of my reaction, I also need to add 4 OH minuses to my right-hand side of my reaction. So those guys are going to combine on the left-hand side to make 4 water molecules. And I'm going to be left with the excess OH minus on the right. So here's my other half reaction. MnO4 minus plus 4H2O becoming MnO2 plus 2H2O plus 4OH minus. Now you have the choice right now here to start combining and reducing water molecules. So you can see here I've got 1 water molecule on the left and I have 2 on the right, so we could reduce that. I just wait and do all of my combining and reducing at the end, but it totally doesn't matter. You could do it now if you wanted to. So this is my only extra step in my process, is getting rid of those H pluses with OH minus added to both sides. Now we just get to go right back to our normal steps for balancing. Just like we did in acidic solution, our next step would be to balance charge by adding electrons. So let's figure out what my charges are on both sides of these reactions. So let's see here. On this left-hand side, I've got 2 minus and a 1 minus. So I have a 3 minus on this side. And I only have a 1 minus on this side. So this half reaction is going to need 2 electrons on the right in order to get to a 3 minus charge. And if I'm looking at this other half reaction here, let's see, I've got a 1 minus on this side for my MnO4 1 minus, and I have 4 minus on the right for my hydroxide. So to make these equal, this reaction is going to need 3 electrons on the left, right? So if I wanted to rewrite those, goodness gracious, I could rewrite these whole things if we want to. You know what, I don't need to. You guys can see it, right? So like here's one of my half reactions with the electrons included. Okay. And here's my other half reaction with the electrons included. So just imagine that I rewrote those half reactions underneath step 5, but I'm not going to bother. Okay, now jumping on to step 6, I want to make electrons equal with coefficients. So I have 2 electrons in this half reaction and 3 electrons in that half reaction. So this half reaction is going to need to be multiplied through times 3, and this half reaction is going to need to be multiplied through by 2. So I will go ahead and rewrite those now. So 3 Cn minus plus 3 H2O. Just have to be so careful. I probably already made a mistake somewhere. 6 OH minus 3 CNO minus 6 H2O and 6 electrons. Okay, let's multiply this guy through by 2. So 6 electrons, 2 MnO4 minus, plus 8 H2O. It's gonna feel so good when it's all done, you guys. Stick with me here. You know it's tedious, but it's also kind of fun. What am I doing? I'm multiplying through by 2. 2 times 2 is 4 waters. And lastly, 8 OH minuses. That's a doozy. Those are just my 2 half reactions, you guys. Now we need to combine and reduce. Now, instead of like rewriting it all into one giant equation, I'm just going to kind of like, I think I'm going to combine and reduce a little bit in my head off of these reactions up here. So like, let's take a look here at this first half reaction. So see how like these 3 waters would reduce this water to 3, right? And maybe we can reduce some waters, combine and reduce some waters in my other half reactions. So like these 4 waters will totally cancel out and reduce this guy to 4 waters. And we can see that the electrons that are on the right-hand side of this reaction will cancel with the electrons that are on the, did I say the correct? I might have called this the left. This is the right. I'm not sure what I said. These electrons are going to cancel with those electrons. And then if you're really clever, you might see here, now I've got 4 waters on the left-hand side of my overall reaction if I was combining these. And I have 3 waters here on the right-hand side of this half reaction. So those are going to end up, this guy is going to cancel to no waters left at all, right? So no waters, and this guy will cancel down to just 1 water. And take a look at these hydroxides. See how I have 6 hydroxides on the left-hand side of this half reaction, and I have 8 hydroxides over here. All of those hydroxides will cancel, and this hydroxide will reduce to 2. So if you want, you can kind of do your reducing when they're in this half reaction state, if you'd like. And now I'm going to rewrite the whole thing and see if I've combined and reduced everything, and hopefully, oh my gosh, I hope I have the right final answer. Okay, so on my left-hand side, I have 3 Cn minus plus 2 MnO4 minus plus 1 water. And on my right-hand side, I have 3 CnO minus plus 2 MnO2 plus 2 OH minus. Oh gosh, let's hope that's right. 3, 2, 1, yes. 3, 2, 2. We did it. Woo! Good job, you guys. You made it through a very long and tedious lesson on redox reactions. What are they? Electrons being transferred, identifying oxidation and reduction, oxidizing and reducing agents, and how to balance reactions in acidic and basic solutions. Good job. Stay tuned for voltaic cells in our next Electro lecture. Bye now.